Hi students, in this first video for today, we are now going to talk about how to calculate our temperature changes using our energy. We can do this by using the specific heat capacity, which you will see comes with the letter C. This is the amount of heat or energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. As you can see by our chart here, we have many different substances that are going to absorb many different amounts of energy. The molar heat capacity is then looking at it from the idea of 1 mole. So if you're looking at these two values, you can see that we have C, or it will be labeled as C mole. The only difference is the amount of the substance. For specific heat, it will be using 1 gram. So as you can see in our units of our chart, these are going to be specific heats because we look for 1 gram of our aluminum or carbon or calcium. If we are going to use the molar heat capacity, then you would need to multiply these values by the number of grams per mole, and you would get a much larger value. But this now tells you on a mole to mole basis just how much energy needs to go in. So if we are trying to calculate the heat absorbed or released, we are going to use the equation Q equals mc delta T. In many cases, if we want to worry about our molar energy, we can then use our molar heat capacity where you see a C mole. But now you will notice that I don't need a mass. This can be done on a per mole basis. So as we look at these two equations, you will see that for M, that is our mass in grams, times our specific heat, times our change in temperature. This is final minus initial because this is a state function. If we are going to use the molar heat capacity, we are just going to take our C mole and multiply it by our change in temperature. Once again, because temperature is a state function, we are allowed to use final minus initial. This is going to become ever important because this is going to give us a sign which will help us indicate if energy is being absorbed or released. So let's try this example. A 466 gram sample of water is heated from 8.50 degrees C to 74.6 degrees C. Calculate the amount of heat absorbed in kilojoules by the water. So the first thing that we are going to want to do is get our equation of Q equals mc delta T. The reason that this question is so important is that we are going to introduce the one specific heat you're expected to know, and that is water. So the first thing that we need to do is go and get our mass of our water, which is 466 grams. And then I need to get the specific heat of liquid water. It is an important note for you to know that if we change phases, we are going to have different specific heats. So not only must you know what species it is, but what phase it is in. For liquid water, the specific heat is 4.184 joules per gram degree C. This is a value that I expect for you to know. So then what I can do is do my final minus initial. So in this case, we see that my final temperature is higher. So this will go first and will be 74.60 degrees C minus my 8.50 degrees C. And that will give me my change in temperature. If I were to go and put this into the calculator, I would get a value of 128,880 joules of energy. Notice that the sign of this is positive. This is indicative of energy being absorbed, which we see here in our question. But seeing I have joules and it asks for it in kilojoules, we would need to go and convert this, and with correct sig figs, you would get a value of 129 kilojoules of energy. This is how much energy our water absorbed. Let's go ahead and try this example. A 14.6 gram sample of brick used in the construction of pizza ovens gains 2,976 joules of heat. What is the initial temperature of the brick if the final temperature is 275 degrees C? So what we end up needing to do here is go and manipulate our Q equals MC delta T equation. So now what I must do is go and not call it just delta T, but it is better for us to now say that it is temperature final minus my temperature initial. Then what I will do is divide out my MC from the right side and put it on the left. So I will now get Q divided by MC equals my T final minus my T initial. So seeing that we're solving for T initial, we can bring that to the left side and take our fraction over to the right side. So our last mathematical manipulation will state that T initial equals T final minus my Q divided by M times C. So these are all variables that we have. So let us go and put in our temperature final, which is 275 degrees C, minus our energy in this case, seeing that it was gained, would be 2,976 joules. We will divide that by 14.6 grams. And then we also have our specific heat of brick, which was listed in the problem as 0.840 joules per gram degree C. So notice that our joules and joules would cancel, our grams and grams will cancel. Then we would have degree C on the bottom of a fraction, bringing it to the top. And if I were to go and put all of this into the calculator, I would end up getting a value of 32.3 degrees C. And if we look at our answer choices on the left, you will see that that is answer C. So as you see in this problem, now that we are trying to use energy to help determine temperatures or temperatures to calculate energy, we saw in previous videos that they are not equal to each other, but indicative of each other. So we are going to make sure that we are looking at what energy is absorbed and gained as we do temperature changes. The best well-known temperature changes come in the form of phase changes. So now for the second half of this video, we are going to talk about the different phase changes and how to calculate the energy of our phase changes and of our temperature changes. So the first thing we need to discuss is the molar heat of fusion. This is the energy required to melt 1 mole of a solid substance at its freezing point. So notice that I am melting a solid into a liquid. This involves energy going in. If I want to then convert my liquid to a gas, this is going to take more energy, and that is when we are going to use the molar heat of vaporization. So now we are going to take that liquid and vaporize it to a gas. What happens if I want to go and freeze something? Well, I would use the molar heat of fusion, but now I would use a negative sign because I am doing the opposite mechanism. If I want to go and take a gas and turn it into a liquid, which is condensation, you are going to need to use the negative value, and we will show you how to do that here in the next few slides. As you can see here, here are some prototypical species going from argon to benzene to ethanol to water, and it shows you the importance of the boiling point and what it means for the heat of vaporization. One does not mean the other, but it gives you a nice ballpark to let you know that if your boiling point is fairly high, your heat of vaporization is going to be fairly high as well. The normal boiling point is the temperature in which a liquid boils when we have one pressure at 1 atmosphere. You're going to see what that means once we get to chapter 11 in the next few lectures. So now let's talk about our different phases. So as you can see here, we are going to melt something very much like the Wizard of Oz. So let us talk about a solid to liquid equilibrium. So notice that I have ice going to liquid water. In this case, you are going from a solid to a liquid, but then freezing is going from my liquid to solid. Notice the difference in the arrows. If I am going from a solid to a liquid, I am absorbing this change in energy. If I'm going from a liquid to a solid, I'm going to have to lose that energy, and we would end up having a negative for our heat of fusion. It's really important that you remember which direction that you are going. So now let's talk about boiling. In this case, this is the liquid to gas equilibrium. So you will see that going from a liquid to a gas is vaporization, but then from the gas to the liquid is condensation. So as we are going from the liquid to gas, we are gaining that energy, meaning it would be an endothermic process and it would be positive, while going from the gas to the liquid is a loss of energy of that species to the surroundings, and we would expect a negative sign for that heat of vaporization. So remember, if we are going from fusion or vaporization, you are to expect the sign of your delta H to be positive. If we are freezing or condensing, this means that we are expecting it to be negative because we are losing that energy to the surroundings. The final phase change that we want to discuss is typically what we call the direct phase change or the solid to gas equilibrium. This is seen with carbon dioxide going from dry ice all the way to the gaseous vapor that you see for Halloween, and that is going from a solid to a gas, and we call that sublimation. The opposite of that is called deposition. So if we want to go from a solid immediately to a gas, like dry ice, we would end up having to add the heat of fusion and the heat of vaporization together to get the heat of sublimation. This is done at a very narrow temperature window. But if I had my carbon dioxide vapor and I were to get the temperature low enough, it would go and do a deposition to go back and form our solid dry ice. Once again, as we are going and reducing that temperature, we are expecting that value to have a negative as well. So as you've seen here, phase changes are incredibly important. But these are not the only things that we need to concern ourselves when dealing with our heating curves. This is a prototypical heating curve. Notice that you have some slanted lines and some horizontal flat lines. It's important that you know each one of these steps along the way. So as you can see, before we get to our species A or point A, I have a solid. That diagonal line is based off the specific heat of my solid. So if I were to go and change the temperature from any point here at the beginning, going to A, I would end up determining the energy going in as Q equals M, our mass of our solid, times RC, but in this case, I will put an S in there for solid, times our temperature change. So this is a really nice use of MC delta T. But notice that once we get to A going to B, we do not have a temperature change. During phase changes, all of the energy put in is going to change the phase, not change the temperature. So we are not allowed to use MC delta T. So what am I allowed to use when I am going and doing my phase change? Well, the energy is going to be Q equals the number of moles doing that phase change times my heat of fusion. So now you are going to see that in this case, I must use a different formula. When we are going from a solid to a liquid, you will use the heat of fusion. If we were to go from a liquid to solid, in this case B to A, the only difference would be is that we are going to use the negative delta H of our fusion. So once we get to B, you will notice once again that I am going to have an increase in temperature, and this will allow us to use Q equals mc delta T. But in this case, our C has changed because our phase has changed. So now what we would use is the liquid specific heat. The mass is the same, and our temperature change would be different. And you will notice that I go and do the temperature change from the melting point to the boiling point. Anytime you get to one of those temperatures, you must stop, do that calculation, and then worry about your phase change. So then finally, let us go and look at point C to D. Notice that it's horizontal, meaning no temperature change. So this means that I would have to use my Q equals my moles times, and because we are going from liquid to vapor, we are needing to use our delta H of vaporization. Our last part, which is going to be just our vapor alone, is going to be our Q equals mc, but now this time we must use the specific heat of the vapor times our delta T, and we can go and calculate that heat. So notice that there are really 5 individual zones of heating curves. On your homework, quizzes, and exams, don't be surprised that we might ask you to do 3 of these 5 or 2 of these 5. You always want to know where you're starting on a heating curve so that you know how many steps to do. There's a really important information based off of some of the lines in your heating curve. The first attention that I want to bring to you is notice that here between A and B and C and D have different lengths. Notice that my heat of vaporization should be a higher quantity, so that is why the line is longer. So as you see your heating curve, if you notice that your horizontal line is longer, this means that more energy was needed for that phase change, and that means that that specific delta H is going to be greater. Finally, let us go and look at all of our diagonal lines. If our masses are all the same in this type of problem, it's important to note that the slope of the line is going to come from your C value. If we are going to have our MC delta T's, we must be very concerned about what our C value means. So in the case of our C, remember that this has the units of joules per gram degree C. Well, if the number of grams is the same, we need to think about the joules. So if you have a large C value, this is going to result in a shallow slope. The reason this is true is that if we have a large C value, it takes more energy, more joules to accomplish that temperature change. If I have a small C value, I will end up getting a much higher slope. So we are able to go and look at the slopes of our lines and determine the various C values. So as you can see here with our vapor, notice how high and how much more aggressive that slope is. That is going to be indicative of a small specific heat. When we go all the way down here to the solid, you will notice that it's a shallower slope. So this would mean that our C value, our specific heat, is probably going to be a fairly large number comparative to that of our vapor. This is really important that you look for such tall tale identities inside of your various heating curves. So let's try a couple of examples. In each one of these, you're going to see that there are multiple steps that we need to go and work together. Calculate the amount of energy needed to heat 346 grams of liquid water from 0 degrees to 182 degrees C. Now, many of you are probably going to look at this and say, this is going to be an easy MC delta T. That is not the case, because inside of here, there's going to be a phase change that occurs at 100 degrees C. So we are able to do an MC delta T to get to that point. Then we need to do a phase change, and then we can take our 100 degrees C up to 182. This means that we are needing to do 3 parts in which we are able to add the energy together. So the first one that we are going to do is go from 0 to 100 degrees C, which is going to be our boiling point. So we are allowed to use Q equals MC delta T. So now we have our mass of our water, which is 346 grams. We have our specific heat of water that is listed, so that is 4.184 joules per gram degree C. And we are going to have a temperature change of 100 as our final, minus 0 as our initial. And we are able to calculate the number of joules that will take us from 0 to 100 degrees. If I put this into a calculator, I will end up getting 144,766 joules. Well, seeing that it's asking for our answer in kilojoules, let us go ahead and convert that to 144.8 kilojoules to accomplish that first step. So now let's go ahead and look at the second step. So at 100 degrees C, we are now going to do a phase change. So this means that we need to go ahead and convert our grams to moles, and we have to use our molar heat of vaporization. So this is best stating that Q is equal to our mole times our delta H of vaporization. So the first thing we need to do to go and get moles is take our 346 grams and divide by the molar mass of water. So that is 18.02 grams per mole. And then we will need to go and multiply by the delta H of vaporization for water. This is where I tell you that you do not need to memorize any of the heats of vaporization or fusion. They would be given to you in your exams. So if we take that math and multiply it by 40.79 kilojoules per mole, you would end up getting a Q for this phase change to be 783.2 kilojoules. So now what we have at 100 degrees is now vapor. We have done the temperature change to get it to the boundary. Now we have done the phase change. Now we must go and raise that vapor from 100 degrees C to 182 degrees C. So that means that we are going to have to do one final step. So if I go from 100 to 182 degrees C, I'm allowed to use MC delta T. So I have Q equals MC delta T. Our mass is the same, so that is going to be our 346 grams. Now our specific heat has changed because I have water vapor. So this is going to be 1.99 joules per gram degree C, and our temperature change is going to be 182 degrees C minus our 100 degrees C. If I do this, I will get a number of joules of 56,460 joules. Or if I were to go and convert it, I will end up getting 56.5 kilojoules. So now you can see that we have gone and done the individual steps. So what does that mean? We can now take the additive sum of all 3 steps and put them together. So if I do that, the energy needed for this entire problem is going to be the sum of all of our steps. If I put all of my answers into the calculator, you will see that it will take 984.5 kilojoules for this reaction to be accomplished. Now, notice that in each one of these cases, we had a positive value. The reason this is the case is that we are going in increasing the temperature or doing a phase change that involves fusion or vaporization. What would happen if I wanted to go from 182 down to 0? I would do all of these steps in reverse, which is kind of nice because the only thing I would need to do is put negative signs. You would get the same amount of energy just with a negative sign because we are undoing what we did. So as our temperature increases, expect for our energy to be positive. And if you see a decrease in temperature, expect for your energy to be negative. Here is the last example for today, and you can see that it is going to be a fairly similar problem to what we just did, and we want to see where we are on our phase diagram. So notice that we are starting with liquid methanol. What we want to do is go to gaseous methanol. So we start at 20 degrees. We are going to 85. The first thing that we notice is that going from a liquid to a gas, we must go through one of our phase boundaries. That is seen here with the boiling point being 65 degrees C. So this means that our first step is going to be going from 20 to 65. Then at 65, we are going to do our phase change. And once we have done the phase change, we can then go from 65 to 85. So notice that I will have 3 steps once again to complete this problem. So from 20 to 65, that is MC delta T. So I can say that Q equals our mass of 4.06. I then have my heat capacity, which is going to be 81.1 joules per gram degree C. And I would have my temperature change, which is 65 minus 20. If I do this, I am going to get a joules of 14,817. And if I convert this, I will get 14.8 kilojoules of energy to accomplish our first step. So now we need to go and do the phase change at our 65 degrees. So what does that mean? Well, the first thing that I need to do is go and take my mass and divide it by the molar mass of my methanol to give us the number of moles. So I can take my 4.06 and divide it by the molar mass, which is 32.042. And now what I will get is a number of moles. So that number of moles is 0.127 moles of my methanol. Now what I need to do is go and multiply this by my heat of vaporization. I'm going from a liquid to a gas. So this means that I will multiply it by 37.0 kilojoules of energy. So for our phase change, you will see that it takes 4.699 kilojoules of energy to accomplish this phase change. So the last thing that we need to do now is go and take our vapor and raise it to the temperature of 85 degrees C. So now, because I have a temperature change that is MC delta T, our mass has remained the same, so that is 4.06. However, our specific heat has changed. Notice that I am using a gas now, so I must have 43.9 joules per gram degree C. And my temperature change going from 85 to 65 is 20 degrees C. If I were to go and calculate this, I end up getting a value of 3,560 joules, which we then know is 3.56 kilojoules. So now we have the individual steps, and the only thing we need to do is go and add them together. So if I add my 14.8, my 4.699, and my 3.56, you will come out to an answer of 23.06 kilojoules. If I look at my possible answer choices, you will see that that is going to be answer B. In this video, you saw the power of MC delta T, not only when dealing with temperature changes of one phase, but as we are going through many different heating curves, showing you when you are allowed to use MC delta T or when you must use the heat of vaporization or fusion. This equation is going to be used exclusively when we are going on to our next video when we are dealing with calorimetry. Have a great day.